Here is an example problem you can play with from week 8, class 15. I think it's slide 14. What we have is a space vehicle. You're in a space vehicle here in the green orbit, that orbit. And the space station is also in the orbit. And you are 500 kilometers behind it trying to catch up to it. Quiz 15 has a similar problem. You're given the distance, 2,337 kilometers, you're behind the satellite, but you're given the velocity also. So if you're given the distance and the velocity, you just divide the distance you're behind by the velocity. Don't forget to convert to meters. Use everything in meters. And you should get that you are 600 seconds behind the satellite, or 10 minutes. You're 10 minutes behind the satellite. And the idea then is to catch up. The period then is going to be 600 seconds less than the period of the orbit that's given, and you're given the period for the green orbit. You're given to it as 42,541.7 seconds. The last time we did this with the ISS, it was 66 seconds, but the analogy is the same. So if I make my period of the red orbit 66 seconds less than the period of the green orbit, then after one orbit I will perfectly line up. In other words, the ISS will take 5,668 seconds. If I subtract 66 seconds from that and fly the red orbit in 5,602 seconds, 5,602 seconds, I will exactly line up with the ISS after one revolution of the red. In quiz 15, the problem's the same. The red orbit is 600 seconds less than the green orbit, so we know what it is. And now we just have to find the apogee and the perigee in distances, and then use the formulas to find the velocity at apogee and perigee. That would give me dVs. So once we know the period of the red elliptical arc, we can solve for A, the half major radius, right? Using that formula for period, from the period, and solve for A. And that's what this solution would look like. You square both sides and then isolate A, which would be the cube root, the cube root of this expression here. And you also know that the Earth is one of the focal points of the red ellipse. The Earth is one of the focal points. Then if you take 2a minus RA, you'll get the perigee distance. You'll get the perigee distance that's up to the shorter end of the arc. Now once you know RA and RP for the red elliptical orbit, you can use the formulas that we developed in class, or that are on my board behind me, for the velocities that depend on RP and RA. Those two formulas will give you the velocity at the apogee and at the perigee. You'd have the two velocities at the apogee and the perigee of the red elliptical orbits. Then once you have those velocities, you simply subtract from the velocity from the green orbit, and that would give you your delta V that you needed to apply. Delta V1 to get into the red elliptical orbit, and then delta V2 to re-emerge and get back into the green orbit after you rendezvous with the ISS. All right, once you have the delta V's, you can use the Tsiolkovsky's equation to compute the propellant that has to be fueled, the propellant mass fraction. In this case, the number is very small, so I'm going to do it with a calculator. So I hit select E, and that's going to be to the power of minus 0.01. So I'll put 0.01 in with a minus sign, and then let's see what that propellant mass fraction equation gives me. If I use the actual equation, it's going to come out to be, looks like 99%. So only 1% of my propellant has to be fuel for this transfer. Well, that sums up what you need to know for quiz 15, from quiz 15. There's a good prep for the week 10 exam or the final exam. Good prep. Any questions on these things, give me an email or send me an email. Don't forget, we also had another video at the URL is shown here, which is from week 8, that covered these same concepts. Well, good luck. Good luck with your other courses, and I hope you have a great holiday season. Thank you. Good luck.